To this part of divergence theorem. In this part, we want to solve this example where we need to calculate the flux of this vector field where S is the surface bounded by the paraboloid x equal 1 minus x squared minus y squared and the xy plane. So the first thing first, we will state what is the divergence theorem. Here, the divergence theorem is calculating the flux of f dot ds, and by the divergence theorem we get this integral will turn out to be triple integral over a region E for the depth of f dv. So we turn the double integral of the surface integral, the flux, into a triple integral where we just need to bound the x and y and z and calculate the triple integral. So the first step, let's find what's the divergence here. Remember, the divergence is we take the derivative of x, derivative of y, derivative of z, and we add them together. So here we will get, for the divergence, we will get 6x squared plus 3y cubed, 3y squared, sorry, plus, and the third one also would be 3y squared dv, which is the same exactly as the triple integral of 6x squared plus y squared dv by taking 6 as common factor. If we have 3y squared and 3y squared, we take 6 as the common factor. So we reach here. What we need to do next is we need to sketch this region and identify my solid E. Now, this region consists of the following. It's a paraboloid, this one, this, and this paraboloid is starting at 1 and it goes down. So something like this. This is my paraboloid. So this is my paraboloid, 1 z equal 1 minus x squared minus y squared. Now, if we start first to bound the z, so I want to know what z is between what and what, we will look that we start with z from the curve itself and we go all down to the bottom, which is exactly z equal to 0. So the bound here will be from 0 to this function here, to the paraboloid, and that's my bound for z. So once I find the bound of z, that will make my integral goes from triple integral into a double integral. So I will do the integration from z to 1 minus x squared minus y squared for the function 6x squared plus y squared dz, and then I will continue later finding the integral with respect to dA. So this integral, the one in white, can wait for now. Let us evaluate the integral in green, which will be 6x squared plus y squared z, and I evaluate z from 0 to 1 minus x squared minus y squared. And now if we evaluate this one here, 6x squared plus y squared, and now for the z I will substitute it by 1 minus x squared minus y squared dA, which turn out to be an integral between x and y. So we have to sketch the region that is between x and y, and we evaluate everything on that region. Now, if we look at the region between x and y, I'm looking at the xy plane, which means z equal to 0. Now, what happened in this region is I'm taking all my value inside this circle down here. So if we substitute z equal to 0, we get a circle, 1 minus x squared minus y squared, and my x and y are coming from inside the circle. So if we sketch it here, it will be just, this one would be 1 equal x squared plus y squared. which if we have this region and I'm doing the double integral, that means I'm taking the polar coordinates, so I will switch the polar coordinates are between 0 and 1, and theta will be between 0 and 2 pi. So this integral up here would be equal to integral from 0 to 2 pi, integral from 0 to 1, and here I have 6r squared 1 minus r squared, because remember x squared plus y squared, if I take the minus as common factor, will get me r squared. And then there is an extra factor of r dr d theta. Now this is an integral that we need to evaluate. So if we evaluate this one from 0 to 2 pi, integral from 0 to 1, if we evaluate this one, I have r squared. If we multiply it by 1, I'll get 6r cubed minus 6r power 5 dr d theta, which is integral from 0 to 2 pi. This one would be 6 over 4 r4 minus r power 6 from 0 to 1 d theta, which is, if we evaluate at 0 and 1, this will be just half d theta. And finally, this integral will be just equal to pi. So that's the flux. That's how we use the divergence theorem to change from surface integral to find the flux into a triple integral, which is easy to be found here. Thank you for watching.